In this video, we will learn about radioactivity, what it is, how it was discovered, the types, uses and effects of radiation. Let's begin with the discovery of radioactivity. In 1896, the scientist Henri Becquerel was studying the properties of newly discovered X-rays. He knew that X-rays made an impression on photographic paper. He planned to expose a uranium-containing fluorescent mineral salt to sunlight. He thought the salt would absorb sunlight energy and then emit energy as X-rays onto photographic paper. This would leave specific impressions or markings or patterns on the photographic paper. But the day he chose to do his experiment was cloudy, so he just put the salts and photographic paper in a desk drawer together. Even though he didn't do the experiment as planned, he decided to develop the photographic paper anyway. And to his surprise, there were impressions or markings on the paper, even though he hadn't exposed the uranium salts to sunlight. He realized that the uranium in the salts emits a form of radiation all by itself, without first needing to absorb sunlight energy. And this was the discovery of radioactivity. And Becquerel won a Nobel Prize in 1903 for this discovery. Then later in 1898, a young researcher called Marie Curie was intrigued to study this further. Her husband Pierre even abandoned his own research to join her in investigating this newly discovered phenomenon. Their work led them to the discovery of the elements polonium and radium. It was Marie who first used the term radioactivity. Radioactivity is the spontaneous emission of particles or energy rays by the disintegration of unstable atomic nuclei. The husband and wife team also won a Nobel Prize in 1903, just like Becquerel, for their work on radioactivity. Later, Marie won another Nobel Prize in 1911 for the discovery of polonium and radium. Many scientists have followed in the footsteps of Becquerel and the Curies, and today we know much more about radioactive decay. Now let's have a look at some of the main types of particles produced from radioactive decay. After the discoveries by Becquerel and the Curies, a physicist called Ernest Rutherford did extensive studies on radioactive decay. He showed that there are different kinds of radiation. Together with other researchers, he showed how particles emitted from radioactive materials are sometimes deflected or deviated in a magnetic or electrical field. He showed that different particles emitted from the radioactive substance were deflected in different directions in the field. The rays or particles deflected towards the negatively charged side of the field must have had some positive charge, and these were called alpha rays. Those deflected towards the positively charged side of the field must have had some negative charge. These were called beta rays. Those rays which weren't deflected from the original path were called gamma rays. They had no charge. Other studies then showed how alpha, beta, and gamma rays have different penetrating power. Scientists showed that alpha rays have a low penetrating ability. A piece of paper is enough to stop them in their tracks. They are heavy particles compared to beta particles, and are made of 2 protons and 2 neutrons, which is essentially the same as a helium nucleus, and these particles move slowly. Beta rays or beta particles, however, have a greater penetrating power. They can pass through paper, but are stopped by a thin layer of aluminum. They are lighter than alpha rays, and are composed of tiny high-energy electrons. Beta particles move faster than alpha particles. Gamma rays have a very high penetrating ability. They are largely stopped by a block of lead a few centimeters thick or a meter of concrete. Gamma rays are composed of photons or waves. They move very fast at the speed of light. Note that the terms particle, ray, and radiation are often used interchangeably. Technically, an alpha particle is a particle. Beta particles are particles. But gamma rays are waves. However, we sometimes use these terms interchangeably because of the relationship between mass and energy. Besides alpha, beta, and gamma rays, there are other types of radiation. These include X-rays, neutron radiation, and proton radiation. Before we continue, let's summarize what we've learned so far in a table. Let's compare the particles in terms of type, symbol, nature and charge, approximate mass, speed, and penetrating ability. Alpha, beta, and gamma radiation are given the Greek symbols alpha, beta, and gamma. Alpha particles have 2 protons and 2 neutrons, the same as a helium nucleus. Alpha particles are positively charged. Beta particles are high-energy electrons ejected from the nucleus when a neutron is transformed into a proton. They have a negative charge. And gamma particles are waves or photons which have no charge. They are neutral. The approximate mass of each type of ray, in atomic mass units, is about 4 times the mass of a proton for the alpha particle, about 1,800ths of the proton mass for a beta particle, and we will put a dash for the gamma rays because they are waves. Alpha particles move relatively slow, beta particles faster, and gamma rays very fast at the speed of light. An alpha particle's ability to penetrate is weak. They are easily stopped by a sheet of paper. Beta particles have a medium penetrance, stopped by a thin layer of aluminum, but being able to pass through paper. Gamma rays have a high penetrating ability. They can pass through paper and through aluminum foil, and are mostly stopped by a few centimeters of lead or 1 meter thick concrete. Let's have a closer look at how these rays interact with matter when they penetrate matter. Radiation can be classified as ionizing radiation or non-ionizing radiation. The diagram shows the electromagnetic spectrum, with waves of long wavelength at the left and short wavelength at the right. We can split the spectrum into 2 parts in the ultraviolet region. On the left are the longer wavelengths, which are non-ionizing. On the right are the shorter wavelengths, which are ionizing. Long wavelengths are associated with low frequency and low energy, while short wavelengths have high frequency and high energy. Ionizing radiation is radiation with enough energy to remove an electron from an atom, thus ionizing it. Ionizing radiation can also break molecules into smaller particles. When this happens in the cells of living organisms, the ions or molecule fragments can react with atoms, causing cellular damage. Non-ionizing radiation, however, generally doesn't have enough energy to remove electrons from atoms. However, this type of radiation can still cause some damage to living tissue. The main effect of non-ionizing radiation is burns. Normal daily exposure to non-ionizing radiation isn't considered to be harmful, but the cellular damage from ionizing radiation can cause all sorts of problems in cells. These include free radical damage, DNA mutations, and even cell death. Now, besides some UV waves, X-rays, and gamma rays, particles that are ionizing include alpha, beta, and neutron particles. If we compare alpha, beta, and gamma rays with each other, we will see a trend in the ionizing ability. All these particles have the ability to ionize atoms and cause damage to tissues. But alpha particles have the highest ionizing ability, beta less, and gamma, of the three, the least. Why is this so? Remember, alpha particles are very slow-moving and can be stopped even by a sheet of paper. If radioactive atoms are ingested into the body and emit alpha particles, these particles will be easily stopped by the tissues of the body and remain in the body, giving the alpha particles time to do their damage. While gamma rays, though high in energy, are very fast and can pass straight through biological tissues, spending very little time interacting with atoms and therefore causing less damage. Now we know about how radioactivity was discovered, the three main types of radiation and how they differ, and which are ionizing and non-ionizing. Are there any beneficial uses of ionizing and non-ionizing radiation? There are. Let's have a look. You are probably familiar with many uses of non-ionizing radiation. For example, in communications. Different frequencies of microwaves or radio waves are used in mobile phones and radios. We can cook food using the energy from microwave ovens. The warmth from heat lamps comes from infrared waves. Light and warmth come from the visible light rays and infrared rays from the sun. Ionizing radiation has many uses too. In medicine, we use X-rays for imaging the bones of the body. Gamma rays or X-rays can be used to destroy microorganisms to sterilize medical equipment. Neutron radiation in fission reactions at nuclear power plants generates much energy which is converted into electrical energy. In industry and research, there are many uses for radioactive traces. For example, radioactive isotopes can be used to track and trace fractures in hydraulics, as well as to trace the progress of chemical reactions in chemistry labs and in cells of living organisms in medicine. Now, there are many more uses for ionizing and non-ionizing radiation than we have discussed here. Those using ionizing radiation need to remember that it is potentially very harmful. Strict safety measures are important when using ionizing radiation. Monitoring the levels of exposure to ionizing radiation needs to be continually done by those using it. Following these measures protects the health and safety of workers using this type of radiation. We have finished learning about radiation for this video. Before we summarize, let's have a sneak peek at some radiation from out of this world. Cosmic rays are particles mostly thought to come from solar flares and explosions, as well as from novas and supernovas of other stars. These constantly bombard our planet with high speed and high energy. They cause a variety of chain reactions in our atmosphere. These reactions release many types of particles and even free subatomic particles. We are largely protected from these particles by the Earth's magnetic field and atmosphere. Some of these particles, however, can cause damage to DNA, but many of them just pass straight through our bodies. Now it's time to summarize everything we have learnt. We learnt about the discovery of radioactivity by Henri Becquerel, and how Marie Curie defined radioactivity as the spontaneous emission of penetrating rays or particles from unstable nuclei. We saw that the three main types of radioactive rays are alpha, beta, and gamma rays. We learned that alpha particles resemble the nucleus of a helium atom. They are slow-moving and heavy and have a low penetrating ability. Beta particles are high-energy electrons which move faster than alpha particles, are lighter, and have a medium ability to penetrate materials. And that gamma rays are not particles but photons. They move very fast at the speed of light and are able to penetrate to a high degree, being stopped by several centimeters of lead or a meter of concrete. Lastly, we had a look at the differences between ionizing and non-ionizing radiation, and had a brief look at some of the beneficial uses of these types of radiation.